on this computer. Great. Okay, so let's open up the homework and go through it, which is available on Gradescope entirely. It won't be done through Canvas. It will be, you can get the link through Canvas for Gradescope, but the submission and everything will happen through Gradescope. And the PDF file is also available online on the website. So if you can log into Gradescope or anything, you have the PDF over there. So let's share my screen. Okay, you guys can see the homework. Cool. So it's a math homework, basically. However, every question is framed in the context of chemistry. The first home problem is calculating, what do you calculate here? Change in pressure, and just using the ideal gas law. The second one is working with partial derivatives for something called the van der Waals equation, which we will be talking about today. The third one and the fourth one and the fifth one are very interesting. They are just, if you think about it, it's just a bunch of math. There is a bunch of variables and you have to manipulate things and get relations. So here I'm showing you an example of how your relation should look like. Here it is done for partial T by partial volume. It happens to be that T is temperature and V is volume, and S is something that we will spend a lot of time talking about. It's called entropy. For now, you don't care. It's just some variable. They treat it as just some variable, and you get such a relation, which is called a Maxwell relation, the same Maxwell of physics, of electrodynamics. So complete that over here, complete this here, complete this here. And then you do it looking at three variables at the same time when you complete this. We will be spending so much time talking about Maxwell relations and manipulating it later that once you have done this, it will really simplify all of our lives later. This is a very non-traditional way of doing a homework. Typically, you don't visit Maxwell relations until halfway through PChem. At this point, you have already given up on PChem with a 30% probability, looking at last time's grade distribution. So you will have some familiarity. So I think you will enjoy this homework because it's math, but all from the context of PChem. Gibbs-Duhem equation is also very important in PChem, thermodynamics, material science, geology, you name it, you will be deriving it here. This point, I would like you to take a bit of time and think what you have learned in the first class. You can try to be funny in one of them, but ideally all five should be scientific. Think about the kinetic model of gases, specify all the assumptions in problem number 7. And problem number 8 is calculating root mean squared velocities. So none of these problems require a calculator. In this one, you might argue that you require a calculator, but don't use it. Make an approximate answer. I don't want 1 decimal digit, 2 decimal digit, 1 decimal digit precision is okay, which you can do just by hand. No calculator in this homework. This policy will change in coming homeworks, but since this homework is designed to get your math gears running, there is no point in you doing any Mathematica, MATLAB, Wolfram, whatever for this one. So no calculator is allowed. And trust me, if you try to use a calculator, we can get a sense that you have done it. So please don't do it. Just be honest. We will be grading liberally, and you will have I think you will enjoy it. Okay, so with that, I will stop the screen share for this. And any questions about the homework? I mean, you all have been asking questions on the Slack channel, so just keep doing that. And that's the way to proceed. So, okay, any questions about anything? PChem, live?
Can you go over that analogy for calculating n prime with the box and Vx and delta t, that one?
Yeah, so Eric raised a very good question on Slack regarding the kinetic model calculation. Let me share my screen and we'll start from here. But yeah, that's a good question. So, by the way, I did get a big iPad, but the pencil was screwed up. So now the new iPad needs pencil 2, and that will be delivered only today. So from the next class, I should have a bigger iPad and my writing should be a bit less like a dinosaur playing football. But today you will have to tolerate. Okay. So let's go to this one. So what you're talking about is, in this case, the question he asked is, what about the Vx itself? Was it bigger or smaller? How would we take that into account in counting the number of molecules over here, correct?
Yeah.
So the thing to keep in mind, and this is a subtle argument here, we are really looking at So Jason, by the way, Jason asks, is the homework graded for completeness or correctness? Both. Sorry. Do your best job. Okay, so here, so later we kind of introduced this notion that Vx itself has a probability distribution, but the thing to keep in mind it happens later. At this point, we focus on just one Vx and do all of this for some value of Vx. We don't care what it is. We do it for some value of Vx, and it's only later that we get the probability distribution into account. You could have done the same thing by taking into account that now Vx itself is a random variable and it might have different values and we can work with it here, but that's not how it's done. So it's a subtle point, and I'm happy to talk more with you, Eric, about it on Slack or otherwise, but hopefully that gives you something to think about. Okay, it comes later. It's a question. So anytime, it's a general framework. Think of this. You're trying to derive a theory involving a variable, and this variable can take lots of random values. You can do two things to account for this randomness. You can do it when you're deriving the theory itself, or you can derive a theory and then account for the fact that the variable is random. So here we're doing the latter approach, which is quite common. Okay. Okay, so, and someone asked, is homework handwritten or do you want typed up? Well, you can do either. You really don't have to type up. If it's bothering you, if it's distracting you from your life, then please don't type it up. You're not gonna get any extra points for typing it up. You can handwrite it, but please make it legible. Please, Connor already has thick glasses. How much thicker do you want his glasses to be? And I also have thick glasses. So please write it legibly. Please number them, all the common sense things, number your pages, number your answers. And just like when you deposit a check and take a picture from a phone, make sure everything is well lit and clear. And if not, we will have difficulty. And secondly, please use only Gradescope for submission. If you are, it will happen invariably. It happened even in my graduate class that in spite of a Google form cleanly set up, 2 or 3 students would email me the answers. Some of them would email me 8 emails with 8 different pages. With 10 or 15 students, it's manageable to deal with that. With 102 of you, it's gonna be fun. So please use Gradescope if it's complicating you. If it's complex, we will figure it out together. Okay, any more homework questions? If there are more homework questions, I will just respond to them on Slack later because I wanna get to science now. Cool. Any science questions?
Is N in moles? Is it the density in moles? Because it's going to be
number of atoms here, number of molecules. So if you read Atkins for this part, it tries to confuse you. He tries to confuse you.
But isn't it just like number of molecules or molecules times like molecules per mole? So like it would be in moles overall.
Don't even worry about moles. Moles is a unit. In this case, N is the total number of molecules in the box, and N prime is the fraction of molecules which are in that small region. If you wanted to bring in moles, which is a way of looking at it, but moles is nothing special, it's a unit, okay? So someone's having difficulty in finding Gradescope. I think many of you have succeeded, so please help your colleagues out. Yeah, and I tried to add all of you through Gradescope, but you will find it, and you can do it. It's not bad. Yeah. So the Atkins way of looking at it is a bit confusing. He brings in moles and there is a small n, this and that, but forget about moles. It's just the number of atoms in the box. Okay, thanks. Any more question? Scientific? And also in general, please interrupt me to ask questions. I love the fact that you are all asking questions. I talked to many of my PChem colleagues and they're like, oh, no one's asking any questions. It's so dead. Where is everyone? I'm like, I don't know what you're talking about. We are having a good time in PChem. Okay, so far we talked about ideal gases, right? Nothing talks to each other. Only once in a while they go and hit against the wall. And guess what? Things are not ideal, right? Things do talk to each other. There are lots of interactions going on between the molecules, and ideal gases follow PV is equal to nRT. Another way of writing it is to say P is equal to N by VRT, or P is equal to rho RT, right? Where rho is the density. So this is valid for the limit rho tends to 0. And you can see why I say that. It's not just the math, it makes physical sense, because when the density tends to 0, again, think of Iceland. The probability that you go and bump into someone else starts to go down. Even worse than Iceland, I don't know, Greenland has even less population or something like that. So the probability of two molecules bouncing against each other just goes down. So things tend to become like ideal gases in the low density limit. But almost all the time, things are not ideal gases. If you try to describe water, for example, which has H and O and H, and you try to describe the properties of water molecule using an ideal gas equation, it's going to do a terrible job. Even something like nitrogen or oxygen, trying to describe it through ideal gas law is going to be a terrible, it's not going to work well. So how do we deal with that? How do we come up with equations of state that are valid in general as the density increases much more than 0? So in order to do that, we will think about deviation from ideal gas behavior. This is something regarding which we can spend weeks and weeks talking about it, but I will just give you a flavor for it. And in general, I will mention that there are advanced ways of looking at it, and some of you have already been messaging me separately asking for more advanced ways, and I'm happy to send you material, but I don't want to inflict it upon everyone in the class. So here we will just do it from an intuitive way. So let's think of the potential energy U of R, for an ideal gas. How should it look like? So here I'm talking about U of R on the y-axis and R on the x-axis. So, and let's say our ideal gas molecules have a radius A. Okay, so the radius is A, and we are talking about what is their energy of interaction when they are at a separation R from each other. So this curve, if you try to draw it, will mostly be 0. It will just look like this. There is no interaction. It's 0, except when R approaches the value 2A, when R is equal to 2A, it just shoots up and it becomes infinity, right? So this is a potential energy curve, for ideal gas. It is either 0 or infinite. It has only two values. And this over here is a discontinuity. You might ask what happens exactly at R is equal to 2A. It's discontinuous. And we can deal with it. We can introduce switching functions or sigmoids if we wanted to be mathematically rigorous over here. So if the two molecules are further than 2A apart from each other, so I'm talking about the center of mass distance, if they're further than 2A apart from each other, they practically don't feel each other. And when they come close, they just say, go away, don't come close. But this is not realistic. Most realistic systems tend to have something called attractive forces. The molecules tend to attract each other. The nature of attractive forces are, the origin of attractive forces can be quite varied. They could come from hydrogen bonding. They could come from dipole-dipole interaction, right? Because you have an electron and electronic cloud moving around the nucleus, so you have a dipole moment, right? Due to any asymmetry. So dipole, and these dipoles will interact to each other, will interact with each other. Furthermore, you can have van der Waals interaction. In 482, you talk about the nature of these interactions. Where do they actually come from? How to describe them well. But one thing to keep in mind that at least two of them, they are really quantum mechanical in nature, right? They are not classical. But things like to hang out together, they are not so xenophobic. You know, a real potential energy curve does not look like this. A real potential energy curve is, I'm just going to delete this middle page. come back. A real potential energy curve is going to look something like, it will still be zero at very long distances. So here it's R, here it's U. When I was an undergrad, one of my favorite professors taught me this trick, which has really stayed with me. And that I started my undergrad in 2003. So wow, that's been 17 years ago. That anytime you draw two axes, before drawing the curve, mark the axis. And I would suggest that you guys also take this, you guys and ladies and everyone else take also this into account. So mark the axis. So here we have U of R and we have R. As R tends to infinity, it goes to zero, no problem. Things are not talking to each other. But as you come closer, it becomes negative. And again, as you get very close, it blows up. So this is the, actually, let's talk about this part. This is the repulsion part, that if you bring it too much closer, the molecules will start to repel each other, or atoms will start to repel each other. But this over here is the attractive part. If they're too far apart, they would like to rather get close, and they would get to a certain proximity, and then they will be like, okay, no more. A good equation to describe something like this, a typical equation used for things like this, is of the following form: A by R to the power 12 minus B by R to the power 6. For those of you who are interested, can go and look up as to why do I have these funky 12 and 6 powers. You can actually think of it from first principles by thinking of what is the potential energy of interaction between two dipoles. And what do systems like to do? Later, as we go ahead in thermodynamics, we will study that the statement I'm going to make next is actually wrong. It gets generalized, but for now, you can keep in mind that, yes, QM is quantum mechanics. H psi is equal to E psi, the land of Heisenberg and Schrodinger and Breaking Bad and all those things. So you can derive this R to the power 6 and R to the power 12 expression by first principles, but I'm just drawing a curve here. It doesn't matter what powers do we have. We could take other powers too. But this is the typical behavior you will have. And there will be a minimum in the potential energy. So what I was saying is that in the absence of entropy, in the absence of temperature, we haven't really talked about entropy yet, systems like to minimize their potential energy, right? You're sitting on a chair right now. You're not just jumping up and down. You might do it 2 or 3 times, but how long are you going to do that? You'll sit down in your chair. And at some point you would rather lie down, right? So you want to be in a minimum energy configuration, minimum potential energy configuration. That's what it describes to you here. This potential over here has a name. It's called a Lennard-Jones potential. It's one way of describing a real gas for Lennard-Jones potential. So keep in mind, even this has approximations. This is talking about the interaction between two molecules only as a function of their interatomic separation. Would I be able to describe water using this potential model? Any answers, any thoughts? Would a Lennard-Jones potential where two atoms talk to each other only as a function of the distance between their centers of mass, will such a potential be able to describe water, the most important liquid on this planet? Any thoughts?
No.
Why not? So Liam says dipole-dipole forces are present, and Malgorzata says because of H bonding. That's correct. Those are all correct. But an even simpler explanation is keep in mind that water has a bent structure, right? What matters in water, one of the things you must have read, is the angle. Using such a pair dependence, you would never get angular things, right? You might be able to describe water which is linear if you did something like this. It would get hydrogen bonding wrong, this and that, but you might do a good job if it was linear. But this angular dependence will never come out of this pair dependence. So even this pair model is approximate. In general, when people try to describe real systems, they go beyond pairs. They try to think, how do 3 atoms talk to each other at the same time? So these things are called multi-body interactions. Instead of just looking at two-body interactions. You could look at how 3 atoms talk to each other, how 4 atoms talk to each other. You could, in fact, look at field theoretic pictures and think about how does one atom talk to a field created by all the other atoms in this framework. Nobel Prizes have been awarded for coming up with good descriptions such as this. And there is still scope for more Nobel Prizes. Maybe one of you will go ahead one day and win some. That would be great. But for now, we are not going to talk about the complicated potentials that can exist. I just wanted to give you a flavor. For now, the question is that we have such an interactive model which applies to a system. So let me summarize what I said so far. What I have said so far is that for an ideal gas, the potential is going to look something like this: infinity, U of R versus R, right? And you might ask, why did you draw a line there? It's just for visual aid. There is nothing, it's discontinuous over there. So this is for an ideal gas. For a real gas, it's going to look something like this. So that's fine. We have talked about potential energy. How do we go from potential energy to equation of state? How do we do that, right? That's the big question now. So is it possible to derive PV is equal to nRT? So for example, if the potential energy was ideal gas, which is this curve over here, could we derive PV is equal to nRT from that by first principles? And similarly, if we had a Lennard-Jones or some other, let me not write Lennard-Jones because that's just a model. If we had a real gas, how would this look like? That's the question we are asking. In my statistical mechanics class, Chem 687, I actually derived these from first principles. I will show you how to really go from such a model where U of R is infinity and 0 everywhere else. How do we go from that and derive PV related to nRT? And it's a lot of fun. Those of you who really like PChem, you're most welcome to come and take my Chem 687. In fact, last time I taught it, there was at least one student, Pawan Ravindra, who is in biochemistry, who liked this class so much that he ended up taking 684 and 687. And yeah, so there we talk about these derivations from first principle. Here, I'm just going to give you the formula. And I know that's disappointing for the purists in the group, but I will give you intuition into why that happens. So clearly, this thing is not going to apply for a real gas. Why do I say it's so clear that it's not going to apply? Because think of it, we are saying P is equal to rho times RT, right? And this is just another way of writing PV is equal to nRT. What does this mean? This means that if you keep the temperature constant, T is equal to constant, and double rho. If you double the rho, then P should double, right? This is not going to happen in a real gas. In a real gas, let's think of it this way, and I will give you an intuitive picture for this. So let's say there are 2 of you sitting in a big room, right? And you have had a lot of Red Bull or Diet Coke or Coca-Cola or whatever you youngsters drink these days, and you're bouncing around, hitting the walls, and then I put 2 more of you in the room, right? The pressure will increase. You will start bouncing the wall probably with 2 times as much force in the same time. Then I add 8 of you, then I add 16 of you. As long as the room is big enough, the pressure will keep increasing linearly. But at some point, I will fill in 1,000 of you. Do you think the pressure will be 1,000 times more than just 1 of you? No. What will happen now? You will be so stuck that most of you won't be able to go and get to the walls, right? So hopefully this gives you an intuitive picture that in a real gas, when the molecules talk to each other and it just increasing the density, as you get denser and denser, the pressure won't just increase linearly because you are going to start bombing into things, you are going to hold on to each other, you will not get to the walls, all these things. So this linear behavior of pressure on density is going to apply. Oh yeah, that's my funky English. How would this like? How would this look like? Yeah, I never intended these notes to be trendy, fancy notes. And this is my effort to recreate a blackboard. And trust me, my blackboard would have looked even worse. But maybe I'm underselling myself. This is a discussion that I'm having with all of you. Mostly a monologue, but aim to be a discussion. So hopefully I've given you an intuitive picture now that for real gases, pressure proportional to density will...
Your page is frozen.
Oh yeah. Stop share screen. Maybe it will also stop happening with the once I switch to the newer iPad. Okay, good. So yeah, cool. So for real gases, the pressure is proportional to density, as only if density is small. So in the small limit, as you keep doing this, it will be true. Not true in general. So how do we think of an equation of state for such a real gas in general? So there are two ways of doing it. So there are two approaches. The first one is called a virial equation of state. Again, like I mentioned in graduate statistical mechanics, this can be derived from first principles and it's a lot of fun, but I can't do it here. If you want, I can send you my notes. So how do we do this? The first one is virial equation of state, and the second one is the van der Waals equation of state. Let's first talk about the virial equation of state. Virial equation of state says that look at P is equal to rho RT in this way. Think of it as a Taylor series. What does Taylor series mean? Taylor series says that if you have a function evaluated at a certain point, you can think of deviations from that point if you don't go too far. So virial equation of state, what it does is to add contributions that depend on higher powers of rho. It will add a contribution that depends on rho. And remember, this is inside the brackets, right? So when you multiply it out, it will look like a square in rho. So there is no term in a pressure which exists for zero density. That is something to keep in mind, right? The pressure does not look as P is equal to P naught plus rho RT. And I'm going to ask you this question in one of the midterms or homework, I promise. Is this right or wrong? Give an intuitive picture. And it should be obvious to you, right? Because if the density goes to zero, there is no bombardment against the walls. That is one thing we learned from kinetic model. So this term must always be zero. So we always have the starting term as P is equal to rho RT. But these additional terms can be added now. And as many as you want, it's like a Taylor series, right? So you can keep adding more and more terms. Of course, their coefficients need to be figured out now. And these coefficients will depend themselves on temperature. How these terms vary with the density is something... Oh, I got a viral. Yeah, viral. It's VIRAL. I ask every time where it comes from. I think it's something related to life or something like that. Nothing. Yeah. Don't think too much about it. There is a theorem in classical mechanics which is called virial theorem. That's where it's derived from. So if you go and look up Wikipedia, you can see the page about virial theorem. So, okay, cool. So we are talking about, let's see if we've got anything on chat. Yeah, cool. We are talking about the coefficients here. So these coefficients, the first one is called D of t. Why didn't they start with A of t? Don't ask me. C of t, and you can have more ... other coefficients. These coefficients are called the virial coefficients. So D, C are called virial coefficients. So such an equation of state, it reduces this EOS, equation of state, I'm abbreviating as equation of state, EOS, reduces to ideal gas law as rho tends to zero, right? As rho tends to zero, in the terms inside the bracket, this one will disappear very quickly. This one will also start to disappear. Then this one will disappear and one will dominate. If one is the only term that dominates, you are left with P is equal to rho RT. And otherwise, you can fit complicated behaviors of gases by if you can do a measurement on your gas or your liquid in the lab, you can find the pressure as a function of density at different temperatures, and you can go and fit it, and you can get the equation of state. So in the red box up here, the point I was trying to make is that when you write a Taylor series, in general, when you write a power series, you have terms that could depend on rho to the power 0, rho to the power 1, rho to the power 2. Here in pressure, there is no term that depends on rho to the power 0. If you had a term depending on rho to the power 0, it would mean that at 0 density, you still have a pressure. Okay, now you could talk about the early universe, this and that, and what happens in a black hole, and what happens outside the universe where there is no material. Let's not go into all that. In our nice world in this universe, we need to have something for pressure to be exerted. If the density is exactly 0, what's there to go and bombard against the walls? Therefore, this P naught is always 0. And the first thing we have is P is equal to rho RT. And now we have added extra terms. So virial equation is just a framework of thinking about contributions from density. If you increase the density much more than 0, then you will have to take more and more terms, right? As rho becomes much more than 0, more terms in virial equation of state need.
The screen froze again.
Oh, that's terrible. Sorry about that. So as rho tends to 0, as rho becomes much larger than 0, many more terms in virial equation of state need to be added. You can't just stop at B or C, you might have to go even further. So this is one way of thinking about equation of state of an ideal gas. It's very heuristic if you think about it. It can be done in first principles. Here I did it in a heuristic way. You make measurements of pressure and density and temperature and you fit them and try to get these values. In statistical mechanics, you can actually derive the expression for B and C from first principles. And that's why statistical mechanics is such a beautiful subject. You can just sit with pen and paper, not have anything else, and you can pinpoint. If you had U of R, if you knew what is the functional form of this U of R, what would be the expression for B and C? We can do this, but not in PChem. I hope you all like PChem so much that next year or later you take StatMech and then you will learn this. For now, that's what we have. That's one way of looking at real gases. There is another way of looking at real gases, which some of you must have seen at some point. If not, it's not too complicated. It's called the van der Waals equation of state. So van der Waals was a famous Dutch physicist and a chemist around early 20th century. I believe he visited University of Maryland. He spent some time here. If you go to the building where I have my real office in the Ipst building, you can actually see the apparatus he himself used to use, which have been brought down and kept there. There are his autograph notebooks and things like that. The Ipst building is a bit of a history museum. If you go and see things there, you will find, if you go there, you will find stuff from back ago. Why? So Matthew Laskowski asks, why are the virial coefficients, which are with density terms, dependent on temperature? Good point. Let me try to give you an intuitive picture. The idea being, again, let's go back to the analogy of trying to stuff lots of people in the same room. If the interaction, so why do these terms exist in the first place? The reason these terms exist in the first place is because as you add more and more particles in the system, they talk to each other, right? They talk to each other, they attract each other, they stop you from going and visiting the boundaries of the system. How much do they stop you in principle should not depend on temperature, because U of R here does not have any temperature. It's just U of R. The reason why they depend on temperature is entropy. The number of ways you can arrange systems, the number of particles, and the amount of thermal fluctuation that you have on an average, these parameters vary with temperature. So anytime in physical chemistry, you have something that shows up on dependence on temperature, a good guess of the answer is entropy, must be entropy. No one really knows what entropy is. We will try to figure out what it is, but that's the main answer here, that the number of ways. So let's get to entropy and then maybe we can revisit this point. But even without entropy, you can think about it, is if you heat up the system, maybe, yeah, let's not go funky here. Let's just think from a very pure perspective. So let's say I have added lots of particles in this system and they attract each other. So they cannot no longer go to the walls. But now I increase the temperature. If I increase the temperature, they are jumping more, right? The thermal fluctuation has gone up. We just saw how the root mean square velocity depends on the temperature. So the chance, we can draw a little movie here. At very low temperature, you will be doing something like this, right? You will just be moving, oh, it froze again. No, it did not. You will be moving in the bottom of the basin. As you increase the temperature, let's go to yellow, no, or green, you will be doing more motion, right? Something like this. As you increase the temperature even further, your range of motion will increase even more. And finally, at very high temperature, you might be doing something like this, right? So that's the intuitive answer of why you might go and bombard the walls more if the temperature increases. This couples with the interaction. You are always constrained to be along the attractive basin, but your fluctuations around that basin increase. So hopefully that answers your question, Matt. Okay, so let's talk about van der Waals equation of state. Van der Waals equations of state, and I was telling you about how you can find van der Waals actual equipment in the IPST building, is also derived intuitively. It considers two physical properties. The first one, and we can call it constraints or parameters, whatever you want to call it. The first one it talks about, it says that, well, in an ideal gas, we said that the molecules or the atoms are so small, they are like point particles, right? They're really, really tiny. But what if it's not true? What if we really want to consider the precise radius, or related to radius, the volume of every molecule? So it talks about a term B, which is the volume of each molecule. So we know in perfect gas, we set B tends to 0, right? But here, this is not going to be equal to 0. So it considers this parameter, constraints or parameters. And the second one that it talks about is called A, which is the attraction term that we have been talking about, that a real U of R will have a dip where molecules will like to go and sit next to each other. They would like to be arranged in some sort of proximity to each other, not too close, but not too far either. This accounts, so together with this, we can write down the van der Waals equation of state in a simple way. So let's first just think about B. First, only B. So what would that mean? We have, for an ideal gas, P is equal to nRT by V, right? This is what we had for an ideal gas. The simple change we make here over here is that we subtract NB from here, where N is number of molecules. So the idea being here is that if B was 0, if the volume of each molecule was 0, then any given molecule can explore a volume corresponding to V. But now that you take into account that every molecule has a certain volume of whatever it is, now when you think of this new molecule that is added over here, suddenly it goes like, well, I cannot, you told me I could explore all of V, but that's no longer true because I cannot explore this one, I cannot explore this one, I cannot explore this one. So you have to subtract that out from V, and that's why you have a V minus NB term. So Alex asks if the preferred spacing isn't the molecules bonding to each other, it's just a happy distance to space out, right? That's a very good point, Alex, and thank you for bringing it up. I had forgotten about it. Here, I should also add there could be ionic interactions, there could be covalent interactions, you know, the region, the nature for the source of attractive forces could be even more general. So it could actually be coming from bonding also. It could very well be coming from bonding if you want to describe it. So that raises a very good question. The van der Waals equation of state that we are going to derive now, can it be used to describe a bonded material? I think so. It won't do a wonderful job, but it would do much better than ideal gas. You will have to fit your parameters, B and A. And you know, there is a famous quote about a physicist. It was Wigner or someone else that with 3 parameters, I can fit an elephant, and with 4 parameters, I can make the elephant wiggle its trunk, you know? So if you have 2 or 3 parameters, that's why virial equation of state is so popular. It has given you B, C, D, E, F, as many parameters as you want. I can fit anything that I want with it. Is it correct? I don't know. Maybe I have overfitted. But so it applies to bonded materials also. It can be applied. So this is the first term. If this is the first correction, if you consider only B. So here you have accounted for the fact that this volume, this volume, this volume is excluded. It's no longer available to the red particle, which I just drew. The second term is a bit more subtle, but is kind of nice. We want to account for what will be the effect of attractive forces on the pressure. What should be the effect? Should attractive forces decrease the pressure or increase the pressure? Any thoughts? Why, Kevin, since you answered first? Kevin, you want to take a shot? Kevin, who?
Should I just say it or type it?
Say again.
Yeah, okay. So yeah, if there's attractive forces, they're more likely to interact with each other and less likely to interact with the wall. Like
Precisely, exactly. Correct. Thanks, Kevin. And I hope this does not dissuade you from answering in the future just because I picked you. Good. So attractive forces will decrease the pressure. If you had repulsive forces, they will be like, oh, I want to escape. I really want to escape from this classroom. PChem is terrible. I hate the teacher. Let me get out of here. But if you like PChem, you're like, oh, I don't want to escape through the walls. I'm going to hang in here. Why escape? Which might be the case since I still have 92 of you over here. Last time I taught it physically, I think by the second week, it had become 70% attendance. That's when I had to start giving pop quizzes. And then the attendance picked up. Oh, yeah, I miss pop quizzes. Giving pop quizzes is so much more fun than taking them, as you might realize. So there is going to be a term that decreases the pressure depending on attraction between molecule, and my screen has frozen. Anytime I get quite poetic, my screen freezes. Share screen. Yeah, really hoping this freezing business won't happen with the new iPad. So there is going to be a decrease in the pressure. So this A is going to be positive, typically. B is also positive. So one thing you have to keep in mind is that when you use van der Waals equation of state to fit a given observation of pressure versus density, temperature, these two parameters should be positive. A is also positive, so it will decrease the pressure. The question though is this sufficient, or is this going to have a dependence on density? So it will be proportional to the density, right? If you have low density and attractive forces showed up, it will decrease the pressure a little bit. If you have higher density and attractive forces started to matter, the pressure will decrease even more. A very interesting question here is, should it be just rho or should it be some power of rho? What should N be and why? Anyone wants to think about this with me? Should it be N is equal to 1 or should it be N is equal to 2? I'm giving you two choices. Okay, we are about to finish the class, so I will just tell you. N is equal to 2. So the correct answer here is This term is rho square. You can think of it, well, we had something like that in the virial equation, Taylor series, blah, blah, blah. That's all fine. But here you can see why it is rho square, because it takes two hands to clap, right? Attraction comes from two things talking to each other. You cannot have attraction just with one thing. What's it gonna attract to? So you have the density coming to this one, and you have the density coming due to this one. So if you have double the things, the probability of two things attracting to each other increases as a square dependence. That's why it's rho square. So this one is our Van der Waals equation of state. Normally in books, yeah, it's you can derive this also from a more first principle basis, not as much as Weyl equation of state, but it is what it is. So you account for the fact that there is an excluded volume. So B is what we can call an excluded volume, which is not available to the particles. They cannot really go and sit in that. It decreases the volume you have at your disposal, while A accounts for the attractive forces. And later in this semester, after the second midterm, we are going to look at something very interesting, which I like a lot, which is called phase diagrams. When we talk about phase diagrams, we will revisit these equations of state and look at them from a bit more detail. But for now, you can just keep in mind. So N is, oh, sorry for the notation. This N, I will just remove it from the notes here. So when you look at it, there is a lot of N that I'm using. Sorry for the over usage of N. I was just talking about the power. I should have used K. So this power K must be equal to 2 because of the square dependence, okay? So sorry for the confusion with N. So there is a first N over here. This is the number of molecules, okay? This N is the number of molecules, while this over here is just the power. So later in phase diagrams, we will probably use these real gases and think about what happens in phase diagrams due to that. So this is a good point to stop. Next time, if we are going to really start to talk about first law of thermodynamics, we will talk, and I want you to take some time to look at the first homework, look at the math. If it confuses you, you really need to put in a bit more work before coming to class Friday. The next lecture I like a lot, because the thing that we are going to talk about next time is why is the change in internal energy a state function can be written as the sum of two path functions. So you have two things that are path functions that depend on how you go from A to B, and you add them together, and the theorem says that it will always be a state function. All the path dependence will cancel out. We are going to look at it from a very fundamental perspective. We are going to understand what is the similarity and difference between heat and work. We will try to look at various examples of work done on a system, and we will really get going. So see you Friday. Bye.